Hello, my name is Camasco Lopez, and this is my presentation on the transport layer security. How vulnerable are you? Transport layer security is a cryptographic protocol that we use every day. When surfing TikTok, sending a work email, or attending our Zoom meetings, we use TLS. TLS operates between the application and transport layers inside the session layer of the Open System Interconnect model, also known as the OSI 7-layer model. When remembering the CIA triad algorithm, we get the CIA out of TLS. So there are some secrets to discover. HTTPS connections use TLS. After the TCP handshake has been established, the TLS handshake begins. The TLS handshake uses symmetric and asymmetric cryptography to authenticate peers in the communication. The TLS handshake consists of 7 steps. The first step is the client hello message. This contains randomly generated data that is used to generate a master secret that the encryption will be derived from, as well as other information. The second step is the server hello message to the client. It also sends randomly generated data that will also be used to generate the master secret for the encryption keys, as well as other information too. The server certificate is the third step and contains the server public key. The client also checks the name of the server in the server certificate to verify that the name matches the name used by the client to connect in an effort to prevent replay attacks. On the client side, they send a certificate to the server for client authentication. The fourth step is optional for the server and is only done if the server certificate does not contain an RSA public encryption key. For the client, the fourth step produces a pre-master secret randomly and sends it to the server using an RSA public key provided by the server. The fifth step starts by the client using the pre-master secret. Then both parties will compute the master secret, and this is where the session keys are made. The sixth step is a 1-byte message notifying the client that the server will begin the encryption message. The seventh and final message finishes the handshake and produces the message authentication code tag, also known as the MAC tag, on the hash of the entire exchange to this point. This is an example of how the session key is established. You have the master secret, which is a 48-bit shared value created during the handshake using asymmetric encryption like the Diffie-Hellman algorithm, which is derived from the first 2 steps previously mentioned, with the random client and random server numbers being sent and the pre-master secret being sent. And that's how the master secret's made. And then you go into the derived keys. In this picture, it's called the key block, which consists of the client write MAC secret used to generate the MACs for data from client. And then you have the server write MAC secret, which is used by the server for its MACs. And then you have the client write key and the server write key, which are symmetric encryption keys. And then you have the 2 initialization vectors for block cipher modes like CVC. Each record includes a sequence number, ensuring old messages can't be reused maliciously, guarding against replay attacks. All cryptographic materials are derived from the master secret and are not reused across sessions, ensuring forward secrecy and strong security. The TLS record protocol, this is like the wrapper that encrypts and protects the actual message sent between client and server. The record protocol has 4 stages. The first stage, fragmentation, breaks large data into manageable pieces. You can think of this as folding a piece of paper you're about to put into an envelope. The second stage, compression, is no longer in use for TLS 1.3, making it optional. But this is where the data is compressed. It also opens you up to certain attack vectors. The third stage, message authentication code, as we saw the MAC, is used to ensure the integrity of the data and no tampering has occurred. You can think of the MAC as sealing your envelope with a tamper evidence sticker. And the fourth stage is encryption. This ensures that others cannot read your data, providing confidentiality. Encryption is like putting that letter into a locked mailbox to be sent. Now, TLS has its vulnerabilities. TLS 1.0 and 1.1 have been depreciated as of March 2021. I have personal experience from this because I had to change all of the certificates, TLS certificates, at my old job, literally last minute because we used Microsoft Cloud. Essentially, here we have four different attacks. The Beast attack, which targets TLS 1.0, and it takes advantage by exploiting predictable initialization vectors. The Raccoon attack, which targets TLS 1.2, and it exploits the Diffie-Hellman algorithm. The Crime attack, which exploits compression algorithms. And then the Logjam attack, which downgrades the security of the Diffie-Hellman key exchange. Now we're going to see an example of the Logjam attack. This is the FBI website where they're entering in some information. Author Dit from Hitchhiker's Guide of the Universe. Now, this is the form. They've gone ahead and submitted it. I'm skipping ahead here a little bit for you. Here they mention that it's taken them 2 weeks to do the attack. Give them a moment and they'll highlight it for you. Now I'm going to skip ahead to the actual attack being executed. And here they have everything prepared. And now they're going to run their decryption program. And as you can see, everything's in plain text. And you have the names Author Dent that were extracted from the FBI website. As you saw, it was FBI.gov. So anyone can be victim of this attack. Now, TLS 1.3 was built with security and performance in mind. It helps prevent against these attacks. It drastically simplified the handshake protocol as well. In TLS 1.2, the client and server exchanged multiple messages in several stages. But in TLS 1.3, the server can immediately send its certificate and key share. So as soon as it receives the client's hello, it can begin communication. This means that only one round trip is required to establish secure communication, reducing latency. TLS 1.3 also removes outdated and insecure elements like static RSA, the Diffie-Hellman algorithm, which did not support forward secrecy. Legacy ciphers like RC4 and hashes like MD5 and SHA-1 were also done away with, as well as the compression algorithm, which exposes you to the crime attack, as we saw earlier, and renegotiation, which exposes you to man-in-the-middle attacks. Another important change was the implementation of zero round trip time. This allows clients to send encrypted data immediately after the initial message. Useful for repeat connections, but it opens the door for replay attacks. TLS 1.3 also allows you control on whether you want to allow this feature or not, which is pretty good because you can accept the risk or deny it. Finally, every session in TLS 1.3 automatically includes forward secrecy, meaning that even if a server's private key is compromised later, past sessions stay secure. Here's a list of all of the references I used to create these slides to present this presentation.